The physiological mechanism of skeletal muscle hypertrophy is fundamentally agnostic to the ethical or dietary philosophy of the host organism. It is an entirely mechanical and biochemical process dictated by the availability of specific intracellular substrates and endocrine signals. When an individual adopts a strict vegan or plant-based diet with the intention of increasing muscle mass, they are not facing a biological impossibility, but rather a complex biochemical engineering problem. To understand why vegans often struggle to build and retain skeletal muscle compared to their omnivorous counterparts, one must bypass the superficial counting of total daily protein grams and look directly into the microscopic environment of the muscle fiber, specifically at a kinase enzyme complex known as the mammalian target of rapamycin, or mTOR. In the context of muscle growth, mTOR acts as the absolute master regulatory switch for muscle protein synthesis. You can stimulate the muscle through intense mechanical tension and resistance training, causing microtears in the sarcomeres. But if the mTOR pathway is not chemically activated, the ribosomes will not translate new proteins, and the muscle will not grow. It will merely repair itself back to baseline or even degrade. The biological key that unlocks and activates the mTOR pathway is not total protein, but rather the intracellular concentration of a single specific branched-chain amino acid, leucine. This is the exact point of molecular failure for the vast majority of vegan diets. To flip the mTOR switch and initiate a robust phase of muscle protein synthesis, the blood must experience a rapid spike in amino acids, resulting in a state of hyperaminoacidemia, and specifically, the meal must deliver what is known as the Leucine Threshold. Clinical data indicates that the human body requires approximately 2.5 to 3 grams of pure leucine in a single sitting to fully saturate the mTOR receptors and trigger maximum hypertrophy. Animal-derived proteins, such as whey, beef, and eggs, possess an exceptionally dense leucine profile, making it effortless to hit this threshold with a standard 25-gram serving of protein. Plant proteins, conversely, are notoriously sparse in their leucine density. If a vegan consumes 25 grams of protein from whole sources like lentils or quinoa, they are falling drastically short of the leucine threshold. The mTOR pathway remains dormant. The amino acids consumed are subsequently oxidized for energy or converted into glucose via gluconeogenesis in the liver, rather than being utilized for the structural accretion of new myofibrillar tissue. To achieve the exact same anabolic response as an omnivore, the vegan athlete must actively hyperdose their protein intake, frequently requiring up to 40 or 50 grams of total plant protein in a single meal, simply to extract the requisite 3 grams of leucine necessary to initiate growth. However, simply eating larger quantities of plant matter introduces a secondary, severe biomechanical obstacle. This involves the physical architecture of the plant cell and the complex issue of bioavailability. When you consume a piece of animal tissue, you are eating a matrix that is highly homologous to your own biology. The digestive enzymes in the human stomach and small intestine easily cleave the peptide bonds, resulting in a rapid absorption rate. Plants, however, are fortified by a rigid cellular wall composed of cellulose and hemicellulose. These are fibers that the human gastrointestinal tract lacks the endogenous enzymes to break down. Furthermore, plants have evolved sophisticated chemical defense mechanisms to deter consumption, specifically anti-nutrients. These include phytic acid, tannins, and protease inhibitors like trypsin inhibitors found in high concentrations in soybeans and legumes. When a person consumes a massive bowl of whole beans or grains to meet their protein quota, these trypsin inhibitors actively block the digestive enzymes in the human pancreas from breaking down the proteins. Simultaneously, phytic acid binds to critical minerals like zinc and magnesium, forming insoluble complexes. These complexes are then excreted, preventing the body from utilizing these essential minerals for health. Therefore, if a vegan ingests 40 grams of protein on paper, the presence of the fibrous matrix and anti-nutrients changes the outcome. The splanchnic extraction, the amount of amino acids sequestered by the gut and liver, is incredibly high. This happens long before these nutrients ever reach the systemic circulation. The actual bioavailability of amino acids reaching the skeletal muscle may be as low as 50 to 60% of the total ingested amount. To bypass this digestive prison and engineer a plant-based diet capable of supporting elite hypertrophy, the vegan must strategically utilize protein isolation technology. Protein isolates, such as pea and rice isolate powders, have had the fibrous cellular walls and anti-nutritional factors mechanically and chemically stripped away. This isolation process effectively converts a slow-digesting, highly compromised plant protein into a fast-absorbing, highly bioavailable amino acid slurry. This slurry mimics the kinetic absorption rate of animal whey. But isolation alone does not solve the limiting amino acid profile. Human skeletal muscle requires all 9 essential amino acids to be present simultaneously in the bloodstream for muscle protein synthesis to occur. If even one essential amino acid is missing or severely deficient, the entire ribosomal translation process halts. This is known as the all-or-nothing principle of protein synthesis. Almost all plant proteins have a skewed amino acid profile. Legumes, such as peas and beans, contain adequate lysine but are severely deficient in the sulfur-containing amino acids, methionine and cysteine. Conversely, grains, such as rice and wheat, possess adequate methionine but are severely deficient in lysine. Therefore, relying on a single source of plant protein guarantees a catabolic state due to an amino acid bottleneck. The biochemical solution is complementary protein pairing. By combining a 70-30 ratio of pea protein isolate to brown rice protein isolate, the biological value and the complete essential amino acid profile of the resulting mixture become virtually indistinguishable from whey protein. The methionine deficit of the pea is canceled by the rice, and the lysine deficit of the rice is canceled by the pea, creating a complete, highly bioavailable, hyperanabolic matrix that is entirely devoid of animal products. Yet, providing the structural blocks for muscle tissue is only one parameter of hypertrophy. The other is the endocrine and energetic environment, which in a strict vegan diet presents its own unique set of metabolic hurdles. Muscle growth is a highly energy-demanding process, requiring substantial amounts of adenosine triphosphate not just for the mechanical lifting of weights, but for the enzymatic assembly of new tissue. One of the most critical substrates for rapid ATP regeneration is creatine phosphate. Omnivores absorb substantial amounts of dietary creatine through the consumption of skeletal muscle meat. A vegan diet, by definition, contains 0 dietary creatine. As a result, the intracellular creatine stores in the muscles of a strict vegan are chronically depleted. During heavy resistance training, this depletion manifests as an inability to sustain maximum mechanical tension in the later reps of a set, prematurely fatiguing the muscle before the high-threshold motor units can be recruited and fatigued. This mechanical failure leads to a suboptimal signaling cascade for growth. The exogenous supplementation of synthetic creatine monohydrate is therefore not merely a recommendation for the vegan bodybuilder, but an absolute physiological necessity to equalize the bioenergetic playing field and ensure that the mechanical stimulus is sufficient to command the nervous system to grow new tissue. By saturating these stores, the athlete can finally unlock the full potential of their physiology. This optimization of ATP recycling allows for sustained tension and maximum hypertrophic response. True growth is achieved when bioenergetic precision meets mechanical intensity. Furthermore, the endocrine profile of an individual relying exclusively on a high-fiber, plant-based diet often exhibits shifts that can subtly undermine hypertrophic potential. The excessive consumption of dietary fiber, while beneficial for the gut microbiome and cardiovascular system, has a highly specific interaction with human hormones. Extremely high-fiber diets can increase the hepatic production of sex hormone-binding globulin, or SHBG. SHBG is a glycoprotein that binds tightly to sex hormones, including testosterone, in the bloodstream. While the total testosterone levels of a vegan may be normal or even elevated, A high level of SHBG means that less of that testosterone is free. Less bioavailable testosterone is available to cross the cell membrane, bind to androgen receptors, and promote gene transcription for muscle growth. To combat this unintentional hormonal sequestration, the vegan must meticulously manage their dietary fat intake. Strict plant-based diets eliminate animal fats and cholesterol that form the fundamental sterile backbone of all androgenic hormones. Consequently, the body must rely entirely on endogenous cholesterol synthesis. If caloric intake is too low, or fat drops below 25% of daily calories, the endogenous production of testosterone plummets. The vegan must purposefully ingest dense sources of monounsaturated fatty acids, such as macadamia nuts, avocados, and extra virgin olive oil. Alongside these fats, specific micronutrients like bioavailable zinc picolinate and magnesium bisglycinate are essential. Zinc is a required cofactor for converting androstenedione to testosterone, but phytic acid in plants actively blocks zinc absorption. Without mindful supplementation and aggressive fat profiling, the vegan athlete risks entering a state of chronic endocrine suppression. Despite intense training and optimized protein, the hormonal signal to retain muscle mass may be too weak to overcome the body's catabolic drive. Balance your intake to ensure your hormonal environment supports the hard work you put into your training. In synthesizing this biological reality, it becomes clear that building significant muscle mass on a vegan diet requires a departure from the romanticized notion of simply eating an abundance of whole, natural vegetables and grains. It demands an aggressive, scientifically literate approach to macro and micronutrient engineering. The individual must forcefully manipulate their intracellular signaling by artificially hitting the leucine threshold through heavily concentrated, isolated plant proteins. They must deliberately bypass the digestive barriers and anti-nutritional defenses of the plant kingdom to ensure actual amino acid absorption into the bloodstream. They must chemically combine disparate plant sources to forge a complete amino acid profile, capable of supporting the all-or-nothing requirement of the ribosomes. They must synthetically replace the bioenergetic substrates like creatine that are entirely absent from their food matrix, and they must hyper-manage their lipid and mineral intake to prevent the high-fiber environment from suffocating their free androgen levels. When these stringent, biochemically precise parameters are met, the human body will respond with robust and sustained muscle hypertrophy, proving that while skeletal muscle does not care about the ethical source of its amino acids, it adheres strictly and unforgivingly to the mathematical and chemical laws of human physiology.